Hello, I welcome you all. This problem is coming from the Engineering Mechanics Dynamics 14th edition by RC Hibbeler. In this particular problem, we have been asked to determine the speed when s is equal to 25 meters. Right, so you can read the problem. I'll not read it, you can go through it, but basically what we have been asked is to determine the speed when s is equal to 25 meters. Right, so we do have a crate that weighs or that has a mass of 20 kg, and this particular crate is subjected to a force having a constant direction and magnitude of F equal to 100 newtons. So we can assume that this constant direction also applies to a constant magnitude. And we know that our F is equal to ma, right? Therefore, if F is constant, it means A is also going to be constant, right? Because m is the mass, which is always constant, right? Or a proportionality constant is always a constant. So if F is constant, then we expect the acceleration to be constant. Right, and then we have been told that when s is equal to 15 meters, the crate is moving to the right with a speed of 8 meters per second, and we're being asked to determine the speed when s is equal to 25 meters. So we are going to solve this particular problem by using two methods. The first one for this particular chapter is called the principle of work and energy, right? Where we are told that the kinetic energy, the initial kinetic energy, okay, plus the work done from point A to point 2 is equal to the final kinetic energy, right? This is the equation that we are using. In the second one, we are going to use the equations of motion. Okay, so we use two methods, we should be able to arrive at the same answer. Great, so let's draw the free body diagram. So we have the weight, we do have the normal force, and we have also the friction. Okay, all right, so this is the weight, which is just equal to mg, and this is the normal force, and this is the friction in motion, which is kinetic friction. Then we'll have two components here. We'll have one component in this direction like so, and another in that direction like so, right? Right, so we are going to have two components. So this one is just F sine 30. This one is F cos 30. Let's finish off this. This kinetic friction is equal to mu k n, which is just equal to 0.25 n. N is the normal force. So let's start with case 1. We are dealing with chapter 14, and in this chapter 14 we are dealing with principles of energy, work, energy, and power, right? So for problems where you have forces, velocity, and displacement, you can employ the principle of work and energy to solve it. So for this particular problem, it has velocity, it has forces, it has displacements. So we are going to use the principle of work and energy, but we are also going to solve the same problem using this old method that we have been using in the past videos, which is just the direct equations of motion. So for case 1, we are calling this the principle of work and energy. All right. So what is this particular principle? So the initial kinetic energy, we are calling K1 plus the total work done from point 1 to point 2 is equal to the final kinetic energy. Okay. So this is the method we intend to use. So let's start working out this. So our initial kinetic energy K1 is just equal to 1 divided by 2 m, which is the mass, then V1 squared. Okay, and this is just going to be equal to, so our V1 here is just equal to our V1 is 8 meters per second, and our S1 is 15. Our V2 we don't know, that's what we are looking for, and our S2 is equal to 25 meters. Okay, so this just becomes half m. Our mass is equal to 20 kg, so this is 20 by V1, which is 8 squared, and if we were to work out this 0.5 by 20 by 0.5 by 20 by 8 squared, we get a 640 joules. Then we have KE2, this is half mv2 squared. Okay, 20 and v2 squared, and this we get a 10 v2 squared. Right, and then summation of the total work done in the system, this is just going to be equal to we have the translational force and the displacement, both of them are in the same direction. So this is what we are going to be doing. So if this is the force in the same direction and the displacement in the same direction, we are calling this as positive work. And if the force is in this direction and the displacement in that direction, we are going to call this as negative work. Okay. The same goes with work due to the weight, okay, and so on and so forth. So if they're in the same direction, positive work; in the opposite direction, negative work. All right, so this is the concept that we're going to be using. So here we are going to be integrating, okay, from S1 to S2 of f, this cos 30, yes, okay, this is positive, and then we do have work due to friction, so this one is negative. Displacement is to the right, the force is to the left, they are in the opposite direction. Okay, Fk ds, and then we do have these they are all going to give us 0. So work Okay, I'll write down that point now. So work due to W, due to the normal force, and due to F sine 30, because you don't have any displacement is 0, the work is going to be equal to 0, which I'm going to take note of that. Alright, so we have this component, and this is just going to be equal to, let's work it out. So this is equal to integral from 15 to 25, 100 cos 30 yes, minus 15 to 20 fk. Let's find fk. So I'll say summation of forces in the y equal to MAY, but we do know that our AY is just equal to 0. Okay, so going up in our reference. So what we have, we do have N minus W plus F sine 30 equal to 0. Therefore, our N is just going to be equal to mg minus F sine 30. So our N is just going to be equal to 20 by 9.81, 100 sine 30. Okay, do we have? So 20 by 9.81 minus 100 sine 30. So we have 146.2. Okay, so we know what fk is. It's just 0.25. Here it is by n. So this is 0.25 by n, and our n is 146.2. Yes. Okay. And this we get, let's work out this. When we integrate that, then we'll have 100 cos 30 will come 0.25 by 146.2. This is 25. So we get let me check it again. Sorry, 100 cos 30 by that 0.25 by 146.2. Okay, so I'm getting a 500.5254. Okay, so there we go. Let's plug in the whole equation now. So we said our k E1 plus summation of the total work, and then KE2, this is the kinetic energy. So we have K1, KE1, which is a 640, plus this one, which is a 500.5254, and this one is just a 10 V this. So making our V2 subject to a formula, this is what we get. So we get this. Can make that subject to a formula, and then plug in everything in there, and we'll have a 640 plus 552.54. Then we are dividing it by 10. Then our V2 will just be equal to 640 plus 500.5254 divided by 10, square root of that. So this we get a 10.68 meters per second. Alright, so let's go to the second method, which is case 2. And here we are using the equations of motion. Okay. By using the equations of motion to just create a boundary somewhere here. Right. So there we go. So we'll say summation of forces in the x direction equal to max going in this direction being our reference. We have f cos 30 minus fk equal to max. Okay. And this is just 100 cos 30 minus 0.25 by 146.2 equal to 20 by ax. Okay. Right. So our ax is just going to be equal to 100 cos 30 minus 0.25 by 146.2, then this divided by 20. Therefore, our ax, let's go there. Our ax is just going to be equal to just 100 cos 30. See the second method, 0.25 by 146.2 divided by 20. So this we get a 2.5026. Alright, we've been told here that the force is constant together with the direction, and we know this equation. M is the mass, which is the proportionality constant. So if F is constant, we expect the acceleration to be constant. So therefore, you can simply say this is constant. And if this is constant, we can use this particular equation to work out the unknown. And the unknown here is V. So V naught is just equal to V1, which is equal to 8. A is equal to AX, which is equal to 2.5026, right? We check it once more again. Okay, 5026. And then our S naught is just equal to 15. And then our S is equal to 25. Right. Therefore, our V squared will just be equal to 8 squared plus 2 by 2.5026 25 minus 15. And you can square both sides like so. So what we have finally is our V is just equal to just 8 squared plus 2 by 2.5026 by that square root. So this just becomes a 10.68 meters per second. The displacement the displacement for n w and f sine 30 is 0, and therefore the work is also equal to 0. Alright, I thought of mentioning this. Okay, so that's the reason why we didn't include this in our work equation, this one as well as this one, because their displacements are equal to 0. Alright, so I guess we are done. We found the velocity using the equations of motion and the velocity using the principle of work and energy. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.